Does the following improper integral converge or not? I'm going to make the function kind of complicated looking. Sine of x plus 4 over x squared. Does this converge or diverge? Let's try to answer that question. And let's add a bit of more directions here and prove your answer. Prove it. Doesn't look like this is something that we can literally calculate as a limit. Is it possible to calculate this as a limit? Maybe. I'm not ruling it out. Sometimes I can't tell. The thing that would be difficult about it is the part that the sine of x over x squared. The 4 over x squared would be easy to integrate, but what about the sine of x over x squared? Sine of x plus 4 over x squared. Could Mathematica do this? I'm not completely saying Mathematica can't, but if it can, I'm not sure how to do it. Okay, it can sort of, except what's this? Cos integral? What's that? It's not cosine. It's related to an integral involving cosine. That's why it's there. I'm not going to look up what it is. It does have a numerical value. Seems like Mathematica is saying this integral converges to about 4.5. But is Mathematica really right? Does this really converge, or maybe Mathematica is deceiving us, or is just not programmed to know well enough what's really going on here? To answer the question, we really have to do some guessing. And I'm serious. We have to do some educated guessing. Sine of x plus 4 over x squared, you might say, in a vague, hand-wavy sort of way, acts somewhat similar to, very unprecise mathematical language, acts somewhat similar to what? I'm after a simpler function that this acts somewhat similar to. How about, well, sine of x oscillates between -1 and 1. If I add 4 to that, that oscillates between 3 and 5. The average of 3 and 5 is 4. Let's keep the x squared in the bottom. It acts somewhat similar to that function. And we know that the improper integral of that function from 1 to infinity converges, don't we? We've talked about that kind of example. The p, power of x in the denominator, is 2, bigger than 1. P is bigger than 1. So if we go from 1 to infinity, it's going to converge. If we went from 0 to 1, it would diverge. Or 0 to 2, it would diverge. Any positive number to infinity, though, is going to converge. Therefore, we guess that our integral of sine of x plus 4 over x squared converges. That's our guess. Is it correct? Yes, it is. It does converge. How do you prove it? Let's do that next. Proof of convergence. As before, we need to use the comparison test for improper integrals. The comparison test for improper integrals has 2 parts to it. Here's the statement in the book. This is a theorem. It is true. It says assume the function you're integrating is positive, greater than 0. So in an example, you would have to check that that's true. That's one thing to check. After doing your guessing, apply one of these 2 bullet points. These are two separate theorems, two separate comparison tests. We're trying to show convergence, so we use the first one. We have to find a function g where f is always less than or equal to g. The graph of f is always below the graph of g. And we know the integral of g converges. If these three things, f of x is positive, f of x is less than or equal to g of x, and the integral of g of x converges, this bullet point allows us to conclude that the integral of f converges. That's how you apply a theorem. You check that the hypotheses are true for your example. Then, because of the truth of the theorem, you can apply it and say the conclusion follows. In this case, that our integral converges. But you have to be formal about it in setting it up. This is valuable for you. Valuable to get practice with this right now. It's really going to pay dividends in chapters 9 and 10, especially chapter 9, sequences and series and convergence tests for series. We're going to be doing some proofs there too. Good to get a little practice right now. Start by saying, let f of x be the function we want to integrate. Sine of x plus 4 over x squared. What should I pick for g of x? If I want to apply the strict version of the comparison test that's in the book, I should not use 4 over x squared because sine of x plus 4 can get bigger than 4. The inequality f of x less than or equal to g of x doesn't work. I would just modify it a bit. Sine of x plus 4 is never going to get bigger than 5. Use 5 instead of 4. That's going to be my g of x, whose integral from 1 to infinity I know converges. But we need to verify that f of x is positive for all x and also less than or equal to g of x for all x. That's fairly simple to do. We know since sine of x is always between -1 and 1 for all x, we can say, if I add 4 to everything, that sine of x plus 4 is always between 3 and 5 for all x. It's also true that 0 is less than 3. That's going to be handy here in a second. Therefore, since x squared is positive, I can divide everything by x squared for all x greater than or equal to 1. I picked 1 there because that's my interval of integration from 1 to infinity. We can say that 0 is less than sine of x plus 4 over x squared. And just applying this one inequality, we don't need them both. I can say that's less than or equal to 5 over x squared for all x greater than or equal to 1. Again, my integral is from 1 to infinity. That's why I'm emphasizing the greater than or equal to 1 part. And this is f of x. And this is g of x. Am I done? Not quite. We know the integral from 1 to infinity of g of x, which is the integral from 1 to infinity of 5 over x squared, converges. Take that to the bank. We talked about that last time. P, the power of x in the denominator, is 2, which is bigger than 1. If I go from 1 to infinity, or 2 to infinity, or 3 to infinity, it converges. If I go from 0 to some positive number, it doesn't. It diverges in that case, but that's not what we're doing. Therefore, the integral that we're interested in, the integral from 1 to infinity of sine of x plus 4 over x squared also converges. And you should say a little bit more about why. It's by the comparison test. When we finish a proof, we get excited and either write QED for Latin, saying we're done, or praise the Lord, because we're so happy that we are done. Have to have some sort of celebration. Okay. You might feel like this is overkill. Really? Write all that? Yikes. I don't want to write all that. Please don't make me. Well, if you want to get full credit, you need to do it. It is worth learning how to structure an argument to give a rigorous proof. Because in harder situations, it's harder to give a rigorous proof. And it might even be a faulty proof that you're trying to give. Maybe it's not even a true statement that you think you're trying to prove. And you just don't see where the error is in your logic. And maybe nobody else does either, but there might be an error somewhere. So it's good to get practice with things that are fairly straightforward to give you confidence for how to structure proofs for harder things. It is practical on the job too. You might have to write an email to your boss explaining why you need this new piece of equipment. Effectively prove why you need the new piece of equipment. Use deductive logic. Make assumptions about the market share and what's going to happen if you get the new equipment, and you could effectively prove that you need it. Of course, your boss could still argue with you. Maybe your boss thinks your market share argument is wrong, but it's still a good skill overall.